Okay, let's dive into this. Because for the last 60 years, the entire digital revolution, literally everything, has been powered by a single incredible material, silicon. Every smartphone in your pocket, every supercomputer, every AI accelerator on Earth. It's all built on this one massive promise, that we can just endlessly shrink silicon transistors. But, well, experts are now warning that the free ride is absolutely over. The world's biggest chip makers are quietly preparing for a future after silicon. So welcome to this explainer. We are going to unpack exactly why silicon is hitting a physical brick wall, and honestly, more importantly, we'll break down the mind-bending atomic successors that are already being manufactured to take its place.
To really understand why this huge shift is happening right now, you have to wrap your head around a specific number, 50. A modern transistor gate is now about 50 silicon atoms across. A single silicon atom is roughly 0.2 of a nanometer wide. So this is a massive paradigm shift. We aren't really doing traditional engineering anymore. We are literally counting individual atoms and just hoping they cooperate. And the glaring problem is that at this microscopic scale, the fundamental laws of physics begin to work against us. The atoms, they stop behaving like solid bricks, and they start behaving more like a fog.
And that fuzzy fog brings us to the ultimate roadblock, quantum tunneling. Think of a transistor as a switch, right? Its entire job in life is to be either a 1 or a 0, on or off. But when the barrier holding the electrons back drops below roughly 7 to 10 nanometers, it becomes so incredibly thin that electrons, they don't even wait for the door to open. They just walk straight through the closed wall. Imagine building this massive, super expensive, waterproof concrete dam, only to discover with absolute shock that the water can suddenly pass straight through the solid concrete. Your switch never truly turns off anymore. Your 0 is no longer a clean 0. It's a maybe.
So what happens when billions of transistors on a single chip start leaking current like that? You get a massive, very expensive crisis. The cost of hitting this quantum wall is just staggering. Every single electron that tunnels through a closed gate is energy spent for literally nothing. It generates wasted heat with zero computing power behind it. And that is a huge reason why modern AI data centers are now drinking water and electricity on the scale of small cities. Meanwhile, just to keep trying to shrink silicon down further, the lithography machines have become so absurdly complex that a single new semiconductor fab costs tens of billions of dollars. We are paying exponentially more money for a rapidly shrinking gain.
Section 1. Power players, SiC and GaN.
To solve these massive heat bottlenecks, the industry isn't just looking for one miracle material to do it all. They're looking for specific materials to solve specific problems. When you map out the data and compare traditional silicon to things like gallium nitride and silicon carbide, the difference is night and day, especially when you look at thermal conductivity and electric breakdown field. These wide bandgap materials, they completely outclass regular silicon. Because they have a wider band gap, they can handle massive electric fields and dissipate heat at rates that would simply melt a traditional silicon chip into slag.
And to put that into perspective for the real world, silicon carbide, or SiC, can handle operating voltages up to 1700 volts. When you put SiC into electric vehicle traction inverters, it pushes the efficiency up to an incredible 98 to 99%. It reduces the weight of the cooling systems and physically extends the car's driving range. Then you have gallium nitride, or GaO, which operates at ultra-fast switching frequencies, over 500 kHz, with very low switching loss. That makes GaN the absolute dominant slam-dunk choice for shrinking down our fast chargers, powering 5G base stations, and running high-density power converters in those data centers we talked about.
Section 2. The Diamond Data Center. But as artificial intelligence continues to push power demands to truly unprecedented extremes, researchers are already looking past silicon carbide. We are officially entering the era of ultra-wide bandgap materials, and this brings us to diamond. Yep, companies like Diamond Quanta are announcing some massive findings in diamond fabrication and doping techniques. The diamond advantage is profound. Diamond semiconductors can operate at voltages exceeding 10 kilovolts. By preventing overheating and drastically decreasing the energy spent on cooling systems, diamond-based components are perfectly positioned to significantly enhance the reliability and longevity of massive AI data centers. It allows for incredibly compact chip designs that can actually sustain the intense, blistering computational power required by these complex AI models.
Section 3. 2D materials, 1 atom thick.
So here's the crucial point. While wide bandgap materials like GaN, SiC, and diamond save our data centers from literally melting down, they are primarily power materials. we still absolutely need a completely different successor to replace silicon for the actual logic processing, the thinking part of the chip. To grasp this logic bottleneck, think of it intuitively like this. Trying to shrink silicon further is like trying to write a novel on a grain of rice, using a fat marker. Silicon is the fat marker. We simply ran out of room. What engineers needed wasn't a magical way to shrink silicon, but a material that acts as a fine-tipped pen. And they found it in a class of semiconductors known as 2D materials.
The real standout candidate here is molybdenum disulfide. Let's just call it MOS2 for short. We are no longer talking about 50 atoms across. MOS2 is exactly 1 atomic layer thick. It's basically a single sheet of molybdenum atoms sandwiched between 2 sheets of sulfur atoms, roughly 0.65 nanometers thick. Because the channel is a single atom thick, you can control the electron from above and below with almost nothing in between. The switch turns off, and it stays off. That fatal quantum leak that was killing silicon, these materials barely have it at all.
But here is the breakthrough that truly changes the game. For a long time, 2D materials were just, a really cool physics experiment. But recently, a consortium of IMEC, TSMC, and ASML actually successfully printed complementary 2D transistors on a standard 300mm wafer. And they achieved a 94% operational yield. 94%! That is huge because it proves that atomic-scale logic isn't just a fun lab toy anymore. It is factory-ready and actively moving on to industry roadmaps right now.
Now, it's really important to understand the different engineering strategies at play right now globally. You have companies aggressively pushing 2D materials, which is fundamentally replacing the brick that the wall is made out of. Contrast this with strategies like Huawei's logic folding. Because of geopolitical export sanctions limiting access to ASML's most advanced, extreme ultraviolet lithography machines, companies like Huawei can't easily chase the new atom-thick switches. Instead, they're forced to engineer around the wall. They're taking traditional silicon and folding or stacking it upwards in 3 dimensions to gain density. So one path changes the physics entirely. The other path buys time on the old physics.
Section 4. Silicon's new 3D foundation.
Okay, here is the ultimate twist of this whole explainer. Despite the title, silicon actually isn't disappearing at all. It's just changing jobs. History shows us that revolutionary technologies almost never replace existing ones overnight. They enter quietly, they solve specific bottlenecks, and they integrate. The chips of the 2030s won't be made entirely of a single miracle material. We're heading toward a diverse ecosystem. We'll see processors that combine completely different atomically thin semiconductors, each optimized for different parts of a chip, all working side by side.
Let's walk through how this actually gets built in the real world, through a process called heterogeneous integration. First off, we don't just throw away 60 years of manufacturing perfection. We keep highly refined silicon logic as the foundational base layer. Next, researchers are perfecting low-temperature manufacturing processes. This allows us to flow gases over the wafer without melting the delicate silicon underneath. Third, this breakthrough allows engineers to grow new, atom-thick 2D transistor layers directly on top of the silicon. Finally, this creates a single, vertically integrated 3D structure. Information doesn't have to travel across a wide, flat 2D board anymore. It travels straight up and down. That drastically cuts latency and eliminates so much wasted energy.
So the whole era of simply shrinking the transistor? Yeah, that's pretty much over. The industry is no longer expanding outward. It is expanding upward. Silicon isn't dead. It's just quietly becoming the robust foundation upon which an entirely new atomic architecture is being built. Which leaves us with this final thought for you to chew on. If silicon, the material that gave us the internet and artificial intelligence, just became the basement, what unimaginable speeds are we going to reach when we finally unlock the penthouse? Thanks for joining me on this explainer. Keep your eyes on those atomic layers, and as always, keep learning.